So, what do we mean by rate of a chemical reaction? It's very similar to the rate of travel of a car, right? How fast is it going? Well, chemical reactions are not moving through space, but they are moving from reactants to products. And so what we're measuring is how fast the reaction makes products or uses reactants. That's going to give us the same answer, but sometimes it's easier to look at the reactants disappearing. Other times it's easier to look at the products appearing. So here we have a visual comparison of a reaction with a fast rate and one with a slow rate. And we have little clocks here to indicate the amount of time. So here we're starting with our reactants A and B, and there is no C present. And as time goes on, we see that within this time period, all of the products have disappeared and we've made the products. I said products disappeared, didn't I? All of the reactants have disappeared. In this slow reaction, again, starting with only reactants, but because this reaction occurs much more slowly, in that same amount of time, it has not finished all of the reaction. Some of the pieces have reacted, but not all of them. Does that make sense? So this is a slow reaction, and that's a fast reaction. So rate is how much a quantity changes in a given period of time. So when we talk about, how fast are you driving on the highway, we're talking about miles traveled per hour, right? So speed is the change in distance divided by the change in time, which could be represented as delta x, delta just meaning change in, delta x, change in your distance or position, divided by the change in time. So for a chemical reaction, what we're looking at is the change in concentration, either of a reactant or a product, and then we'll divide that by time. So here we have an example reaction. This is happening in the gas phase. We have hydrogen gas and iodine gas reacting to form another gas. This is a very friendly molecule, right? Hi. It's all caps. It's kind of yelling, right? Hi. Yeah, hydrogen iodide, whatever. Anyway, so the change in concentrations of the reactants is negative because they started at a high value and they're decreasing over time. They're going to end up at 0 maybe, right? So that's going to be negative. But we need to have the rate be a positive number, okay? Because if the rate was negative, then that would suggest that it was maybe going backwards. So by convention, reaction rates are always positive. That's what they just decided. So if we're looking at the reactant concentration, so the change in the concentration of hydrogen, so if you remember, hopefully you learned this in Chem 1A, the brackets here represent the concentration of the thing inside. And usually the units are molarity, almost always. So the molarity of hydrogen, the change in that, divided by the change in time. And when we've got delta, that's always going to be the final value minus the initial value. Because there's a lot of times when the sign really does matter. So the change in concentration for hydrogen is the final concentration, the concentration at whatever the second time is, and we subtract the initial concentration. The concentration is getting smaller and smaller, so this up here is a negative number. Because we need the rate to be positive, we're going to put a negative sign in front of the whole thing, so it becomes positive. The time change, this is, maybe 30 seconds minus 1 second or something, this will always be a positive number. So we can say that the rate of the reaction is the change in the hydrogen concentration divided by the change in time. We could also define it as the change in the concentration of the other reactant divided by the change in time. These rates will be the same. There is one rate for the reaction because the concentration of H2 is changing right along with the concentration of I2. Because if you've got two of these molecules, it's going to use up two of those molecules. So the change in concentration for those will be the same. Any questions? We can also look at the formation of the product. So the change in the product concentration. Well, the product concentration is always increasing, and so that is a positive number. And so we don't need to put a negative in front of this to make our rate positive. It's going to be positive all by itself. So here, positive change in HI divided by the change in time. But two of these are made for every one of those that gets used up. This rate needs to be the same as the other rates. We can only have one rate for a reaction. So we put this coefficient, this factor here of 1/2 in front of it so that we'll get the same rate as before. So this coefficient of 2 becomes a 1/2. When we have one molecule of H2, we're going to get two molecules of HI that form. So we'll get twice as much of this in a given amount of time as this is decreasing. And so that's why we have to take this change and divide by 2. So we include the coefficients in this so that the rates will all match up. We didn't use a coefficient for H2 or I2 because there isn't a written coefficient. I mean, you could put it in there, it's just 1, right? But that's silly to write times 1 over 1. So, said this before, reactant concentrations decrease with time. So, this graph, and we're going to have a lot of graphs in this class, shows the concentration in moles per liter as a function of time in seconds. So if we look at one of the reactants, hydrogen, it starts at a high concentration, and as time goes on, it decreases. The concentration goes down, right? Because it's reacting and disappearing. The red line is the concentration of the product, HI. Well, we started with none of that, and as time goes on, that concentration increases, right? So one is decreasing, the other is increasing. But the HI is increasing twice as fast as the H2 is decreasing. Because of this coefficient, we're making 2 of these for every one of those, so it's going to appear twice as fast. From a graph like this, we can calculate a rate by drawing a tangent to this curve. So notice that these are not linear decreases. Some reactions will have a straight line, but most of them will not. It's some sort of a curve. So if we want to know the rate at this point in time, because the rate might change, we can draw a line that's tangent to the curve and then look at the change in the rise. This is rise over run. It's the slope here. So the change in the concentration of that divided by the change in time, the change in x. And because this is negative, we'd multiply that by -1. So if we do that, I did bring my calculator. So that would be, not that. Try that again. So for the hydrogen, the change was -2.8. Sorry. -0.28 was the change in h, divided by the change in time, which was 40 seconds. So this is molarity, and that's in seconds. And so that's going to give us a number, right? You should always bring your calculator, and you should always get it out and have it ready, because we're going to be doing some math. So negative 0.28 divided by 40. And we get negative 0.007 molarity per second. So that rate of change is negative because the hydrogen ion concentration is getting smaller, not the hydrogen ion, the hydrogen molecule concentration is getting smaller. If we look at what's happening with our little friend Hi, from the graph we can tell that the change is 0.56 over 40 seconds. 0.56 divided by 40 equals 0.014 molarity per second. So the rate at which this is decreasing and the rate at which this is increasing are related by the stoichiometry, the coefficients in the balanced chemical equation. The rate of this increasing is twice as big, right? So 0.014 and 0.007. So we need one rate for the reaction, because otherwise we have to say, well, we're talking in terms of this, in terms of that. It all comes down to the same thing. So the rate of the reaction then would be -1 times the negative 0.007, and that's going to give us 0.007, or 1/2 of 0.014, which also gives us 0.007. Okay. So whether we calculate the rate from the products appearing or the reactants disappearing, we're going to come up with the same number. Any questions? This may seem like kind of basic stuff, but it's really different from what we talked about in Chem 1A. So I don't want to lose anybody here, right? It's okay to be like, what is this? Okay, so feel free to ask questions. Well, oftentimes the average rate changes as the reaction progresses. Let's go back and look at this graph. The rate is the slope at any given point. Well, the slope here is higher than the slope here. So the rate is continually changing. So we can talk about an average rate where we take the change over a period of time, and that would be the average for that time period. So from 0 to 10 seconds, we see this decrease, 0.181. So we take that change and divide it by 10, and we get this as the rate of the reaction. In the next 10-second time period, the change in concentration was only negative 1.49. Divided by 10 again, we get a different rate. So as time goes on, the rate gets slower and slower and slower. And we'll learn probably much more than you want to learn about why that happens. And essentially, if you think about it, in order for the reaction to occur, the reactant molecules have to bump into each other. If there aren't as many reactant molecules present, then it's going to take them longer to find each other. And so they will not be able to react as fast. So this is often seen that the rate decreases as the reaction progresses. It never increases. There are some things that stays the same, but it never increases. So that was an average rate. An average rate is would be taking the concentration at this point and the concentration of that point and dividing by the change. That's going to give you an average over this time period. The instantaneous rate, the rate at that point, we can find by drawing a tangent to the line. We're not actually going to be drawing tangents. It's just like telling you how it happens. So drawing the tangent, we can find the rate at this particular time. And we already did this calculation in a previous slide. So at this time period, looks like 50 seconds, we found the rate by drawing tangents to the line. We're finding the slope at this point. The slope is continually changing. Any questions? So we can generalize our definition of reaction rates. So if we have this generic reaction, the lowercase letters represent the coefficients. Those would be numbers like 2 or 3 or something. The capital letters represent the formulas for the elements or compounds. So A amount of A plus B amount of B forms C amount of C and D amount of D. Well, we can define the rate in terms of the disappearance of A. It is the change in concentration of A divided by the change in time over which that occurs. And then to account for these coefficients, in front of that, we're going to have 1 over the coefficient. This is a reactant, and so we have to put a negative on there because the rate has to be positive. It just occurred to me, well, why don't they just use absolute value? I don't know, but they don't. We could also define it in terms of the concentration of B, which is also decreasing. This is a reactant. So this is going to be a negative number. To make the rate positive, we have to multiply by -1. So the change in concentration divided by the change in time. And we account for the stoichiometry by doing 1 over the coefficient. That's what we did in the previous example where we had 1/2. The coefficient was 2. And so that is being created twice as fast as everything else. So we had to divide by 2. So this is the pattern so that you don't have to stop and think about it. Well, is this twice as fast or half as fast? That can get a little confusing. It's just 1 over the coefficient. So in terms of the reactants, we have a -1. These are products. The changes in concentration are positive, and so we do not need a negative sign. They put a positive here just to point out that this is not negative. But otherwise, it's the same. 1 over the coefficient times the change in that concentration divided by the change in time. Okay? If we can monitor the change in one of these species, one of the reactants, one of the products, then we can figure out what the rate of change is for all of the other things, because they are all related to the same rate. So we can figure out what's happening with other reactants or products right now, but we cannot predict what's going to happen in the future, because this is the instantaneous rate and it's changing. Any questions? Okay, let's do an example. So everybody should be writing here, unless you're on the wait list, and then you should be writing on a piece of paper. I'd like to point out also that these slides are numbered so that you can find them more easily. So like if you don't have the printed out lecture notes, you can just write down slide number 13, and then you'll be able to find it later, right? Okay, so here's a problem. Consider this balanced chemical equation. In the first 10 seconds of the reaction, the concentration of I minus dropped from 1 molar to 0.868 molar. Calculate the average rate of this reaction in this time interval. This is going to be an average because we're not measuring it at one point in time, we're measuring it over a span of time, and so that's why it's an average rate. So the rate of the reaction. So the rate of the reaction is, are we looking at a reactant or a product? I minus. I'm going to stand here until somebody has the guts to say it. Reactant or product? Reactant, thank you. It's a reactant. It's on the left side of the arrow, right? Remember that? So this is a reactant, and so to write the rate equation for reactants, we need a negative sign. And then we're going to have 1 over the coefficient. What's the coefficient for I minus? It's a 3. So 1 over 3. And now I want the change in the I minus concentration divided by the change in the time. So delta is change in, it's the final minus the initial. So we're going to look at the I minus final concentration and subtract the I minus initial concentration. And we're going to divide that by the final time minus the initial time. Okay? Delta is final minus initial. I'm writing this out in way more detail than you would once you get the hang of this. So negative 1/3. And then the final concentration is what it goes to. So that's the 0.868 molar. And we're going to subtract the initial concentration, which is 1.00 molar. And that's going to be divided by the change in time. Well, in the first 10 seconds, what was the initial time? 0. And what's the final time? 10 seconds. Did we really have to do that math? No, we didn't. They told us what delta T was. So all we have to do is find the answer to that. Now, I've noticed that some students have a rather strange relationship with their calculator. This is not math class. If you want to do stuff in your head, that's fine, but you should check it on the calculator. Okay? Kudos to you if you can do mental math. We're not going to mess around with that. We want to use our calculators correctly. So when I'm doing a problem like this, and I'm using my calculator, I want you to get your calculator out and type the numbers in and make sure that you get the same answer that I do. Because I make mistakes. I make more mistakes in Chem 1B than I made in Chem 1A. And isn't it kind of fun to catch the teacher making a mistake? I won't feel bad because everyone makes mistakes, right? What I really hate is when I screw up in a lecture that I'm recording and posting on YouTube, and nobody tells me. And then I find out like 2 years later, somebody on the internet points out, hey dummy, 2 minus 1 is 1, not 2. Oh, I had this whole classroom of students and nobody said anything. Sometimes what you get is wrong and what I'm getting is right, and so you'll say, well, I think you're wrong, it's this. I will do my very best to not make you feel bad, okay? Because we all make mistakes. So don't be afraid of being wrong and pointing out that I'm wrong, because we're all going to make mistakes all the time, okay? And The reason I want you to do this is because we need to find out if you're miscommunicating with your calculator. As it says in the syllabus, I would encourage everyone to get a 36X Pro Ti. They're about $25, which means that, if you spill acetone on it in lab and destroy it or something, it's not your $100 calculator, right? And this does some amazing things. This is just an amazing little machine. So, do this math on your calculator, and let's see if we can come up with the same answer. I got 0.0044, and the units would be molarity per second. Did you get that number? Anybody get something else? It's your calculator's fault, it's not your fault, and I'll come over and have a word with your calculator. So,
are you going to throw hands with the calculator?
Pardon me?
Are you going to throw hands with the calculator?
I don't know. So when we're doing math like this, we need to be a little bit careful, right? Because when we communicate with your calculator, it doesn't always understand what we mean. So that would be the rate. So any questions? And because I often make mistakes, the answer is up here. So if you're looking at your notes, the answer's right there up in the corner of the slide. So really, if I'm wrong, you have no excuses. Right? I gave you the printout with the correct answer on it. I can't see it until I finish the problem. Right? That was part A. Determine the rate of change in the concentration of H plus during this time interval. Well, we could write an equation describing the change in concentration of H plus. That's the rate of the reaction, right? Rate equals. H plus is also a reactant, so we need that negative sign. And then the coefficient of 2 goes in the denominator. So times 1/2, and this is going to be the change in hydrogen ion concentration divided by the change in time. Same kind of thing that we did for the other one. This question is a little different though. It's not asking for the rate of the reaction, it's asking for the rate of change in concentration of H plus. So it is asking us to find this. So this is what we're trying to calculate. We aren't given any information about that. So we have a 1 and a 2, and then we have rate. Well, what's the rate of the reaction? Oh, we just solved for that, right? So the rate is 0.0044 molarity per second. So negative 1/2 times this thing we're looking for equals that. We just need to solve for what's in the yellow box, right? So we'll multiply both sides by 2 and divide by -1. So I still got that in my calculator, so I'm going to multiply by 2, divide by -1. And I end up with the change in the hydrogen ion concentration, delta H over delta T, is equal to negative 0.0088 molarity per second. Why is it negative? The concentration is going down. The final concentration at any period is going to be less than the initial. It's going to be a negative number. So this has to be a negative number. This rate is twice as fast as that one, isn't it? That's because this is disappearing at twice as fast because of that coefficient. The rate of I minus is going to be 3 times as much. If we did the rate of H2O disappearing, that would match the rate of the reaction. We would just have to make it a negative number. Any questions? Oh, good, I got the answer right again. So now it's asking us to predict the rate of change for H2O2 and for I3 minus during this time interval. Well, the rate, and we know that's 0.0044 because that was what we calculated in part A. That rate, we can make the equation for this other reactant and for the products. So H2O2 is a reactant, and so we need a negative in there. This has no coefficient, so we could say, well, we don't need a fraction here. Other people are like, no, but we have to have the fraction. Okay? It's 1 divided by 1. And then the change in H2O2 divided by the change in time. Yeah? So again, what we're trying to find is not just a single letter X, it's this kind of complicated looking thing. Well, if negative this equals that, then what does this equal? Negative 0.0044, right? So delta H2O2 divided by delta T is going to be negative 0.0044. Any questions about that? Let's look at the I3 minus. So here we're looking at a product. The rate of this reaction is still 0.0044. We're talking about the same time period, same reaction. So writing the equation for this would be plus, not minus. You don't have to write the plus. I just do that to point out that it's not minus. Again, if we want to be really consistent about coefficients, the coefficient for that one is also a 1 times the change in the I3 minus concentration divided by the change in time. And this is the part we're looking at, we're trying to find. So the change in concentration for I3 minus is going to equal what? Positive 0.0044, right? This is one of those things where you're like, it can't be that easy. I mean, look at this. If we just get rid of the 1 over 1, it says it right there. We didn't have to actually do anything, right? So sometimes, just to mess with you, we make it really, really easy. So if something seems easy, it might be easy. The rate of change for this is positive because it's being formed. The rate of change for this one is negative because it is disappearing. It's being destroyed. Any questions? There are the answers. Oh, I was hoping we were done. We'll carry on. Okay, this is a conceptual problem, which means we probably don't need a calculator. For this reaction, A reacting with 2B to form C, under a given set of conditions, the initial rate is 0.1 molarity per second. What is delta B over delta T under the same conditions? What is the change in concentration of B divided by T? So we can just think about this, but then we could get it backwards as well. Because if we look at these answers, we can say, well, this is a reactant, it's supposed to be negative, right? So we can get rid of, I don't want to get rid of it that way, or that way. There we go. We can get rid of that one because it can't be negative. So the choices that we have are the same, half as fast, or twice as fast. We've got that 2 in there, right? But then, it can kind of twist your brain a little bit. Well, am I supposed to multiply by 2 or divide by 2? Let's just write it out and look at it. We don't have to calculate. So the rate is 0.100 molarity per second. And that's going to equal, because this is a reactant, negative 1 over the coefficient times the change in B over the change in T. So again, we are asked for this number. Do I multiply by 2 or divide by 2? Multiply, because this is 1/2 in the denominator, right? It's considered a conceptual question because we don't actually need a calculator. You can just think about it. So then the answer is negative 0.2. This is disappearing twice as fast as A is disappearing. Any questions? That's the answer. My goodness. How do you measure the reaction rate? This is usually not as simple as, we'll just measure something. We have to be able to measure the concentration of one of the components, one of the reactants, one of the products. There's 2 ways to approach the problem. If we have a fast reaction, say it's going to be done in less than an hour, then it would be good to continuously monitor that concentration. If we have something that's going to take a very long time, there are chemical reactions that it might take a week for it to finish. You don't need to be monitoring it the whole time. You could probably come in a couple of times a day and just see where it's at, right? How do we measure the concentration? Well, this is actually a branch of chemistry called analytical chemistry, which is what I got my major in, my master's degree in. And this is really fascinating, at least to me. How do you measure the amount of something that you can't see, is too small even with a microscope? How do you measure how it's changing? That's a puzzle, right? That's a problem to be solved. And people have done a lot of work on this. There's a lot of different ways we can do this. One is polarimetry. So some chemicals are chiral, and they will actually change light as it goes through. So polarized light, and they will twist it. And how much they twist it is dependent on how much of it is in the solution. we're not going to do polarimetry. We could look at the total pressure. If we're doing a gas reaction, the total pressure of that mixture will be related to the partial pressures of the gases, and the partial pressures will be related to their concentrations. So we could do that. Spectroscopy, we will be doing this. This measures the amount of light of a particular wavelength that's absorbed by one component. So a lot of times these will be colored solutions, but it can also work with ones that aren't colored. I think we have an illustration here. So we have some source of light, and we take just some of that. We pass it through a slit and pass it through a prism, and that spreads out the light by wavelength, right? And then we use the monochromator. We can select which color of light we allow to pass through the sample. What color we pick is going to depend on what we're trying to measure, because different chemicals, different elements will absorb different wavelengths of light. So we pass that light through the sample, and we see how much comes through using a detector. This is all hooked up to a computer, and the computer is going to do all the calculating transmission and all of that stuff for us, and it's just going to tell us what it is. So the more of that, here we've got iodine is a reactant, and that's violet in color. And the other two species here are colorless. So the more iodine is in here, the more light is going to get absorbed. And so we're going to have less light come through here. If there's no iodine in here, all the light will go through. So we can use the amount of light that gets through to measure the concentration of this thing. Any questions about that? This is a whole big area of chemistry within analytical chemistry. So those are just 3 examples of how you can measure the concentration. So what if you have a slow reaction and you're going to do periodic sampling? How do you do that? Well, what you're going to do is you're going to take a sample from that reaction mixture at different times. So say that one that takes a week, you're going to get it started, and then maybe 6 hours later, you'll take a little tiny bit out of the reaction mixture, and maybe you're doing spectroscopy, and you'll identify the concentration then. That little bit, that sample, is called an aliquot. Okay. I don't expect you to necessarily use that word, but it's going to come up, and you just need to know an aliquot is just a sample of something. So then we do quantitative analysis on the sample, and we can figure out what the concentration is at that point in time. So for periodic sampling, we can do things like titration. So if it's an acid or a base, maybe, you pull the sample out and you can titrate it just like we did in Chem 1A and find out the concentration. You could use gravimetric analysis. So this is where you may precipitate it into a solid and collect that and weigh it, and from that you can calculate how much is in the sample. Or you can do something like gas chromatography, where you can look at different concentrations of the components in a mixture. Have you a picture of that? Yeah. We have we have spectroscopy in the instrument room, and we also have a gas chromatograph. So the way the gas chromatograph works is you have a carrier gas supply. Oftentimes this is something very inert like helium or nitrogen, and we send it through this long, very, very skinny tube. On the inside of this tube is a substance that your chemical of interest is going to interact with. So as your aliquot goes in here, that thing you're interested in is going to be attracted to what's on the inside of this column. And so it's going to kind of linger. The more attracted it is, the longer it's going to take to go through the column. Something that is not attracted at all will just go straight through. And then you have a detector. There's lots of different kinds of detectors. But you will see when something comes out of the column, because you'll see this peak. The signal will go up and then it'll come down. And it doesn't all stay together, it spreads out, and so that's why you get this, it's not a Gaussian curve, but you get this peak instead of just a line, because it spreads out. But the concentration is related to the area under that peak, and so we can measure it that way.